Hi, my name is Emmett Larson.
Zach Cox.
Brandon Woodward.
This is our tutorial video for our CS340 Program Language Design final project. The goal of our project was to create visualizations of various sorting algorithms. In this section of the video, we'll go through the project files and showcase some of the code that we've written. After that, we'll provide a demonstration of some of the visualizations and sorts we have created.
All right. I will be going over some of the utility functions and the sort class. So if we scroll down, we can see here's our most basic sorting algorithms that we implemented. So there's going to be bubble, selection, quick, and cycle, and merge. Those are your most basic ones and that we implemented. And those, of course, to initialize it, this will, if you enter in an n number of nodes, that's going to be this guy, and then that creates all the different types of nodes between 0 and 1. This is going to, so this one is going to be, you can see there's a couple different cases. This is going to get the actual time, like n to, or n log n or something, O log n. That's what this is going to do. This is basically what all these are calculating. As you can see, there's bubble selection, quick, merge, and cycle. All these have their respective O of n's. And then here's main. This is where all the magic happens. So the majority of this file is going to be the GUI that I made. So a lot of the stuff is basic GUI implementations. You can see this says select a sorting algorithm. Here's the color, more nodes, just kind of basic stuff. This sets up the whole GUI there, and then it sets it to true. These methods are for drop downs, so that's way you can see actually when you start typing in the node box, you can see the seconds kind of change, kind of like that auto submit kind of stuff. That's what I'm implemented. There's them actually being run right there. Here's the eject button. So this guy, when you click submit at the end of typing everything in, it will then submit the code, and then it will then run the sorting algorithm to the respective things that you selected. Send them more canvas. So this, now down here, all this stuff on the bottom, this is going to be all running the sorting algorithm. As you can see later, so actions performed, some more GUI elements there. And then again here, more GUI elements here.
Okay, now we're going to take a look at some of the sorting algorithms and then also how we set up the parallel processing tasks as well. So I'm not going to be explaining exactly how every single sorting algorithm works, but as you can see here, we have links for explanations for how each sorting algorithms worked. We use these websites. So here we have our selection sort implementation here, and so I'm just going to go over a few things that are kind of universal in each sorting algorithm. So we always pass in this array here, obviously, as that's what is getting sorted. But then we also have this task number and this task total here. These two integers are very useful when we're using this draw sort step function. So later on when we do the demonstration, you'll see that as each element gets sorted, there's a kind of a bar that gets moved along a big row of bars. So we need to know which the number of tasks and the total tasks, what the individual task is and the total task, just so we know the position locations for drawing each sort step. So then this is our implementation here of selection sort. If you want to pause the video and take a look at this, you can. Like I said, there's also Geeks for Geeks selection sort algorithm right here. That is a great resource for finding, for learning about these algorithms and data structures. So then we also have bubble sort here. Again, we have this task number, task total. We have our implementation of bubble sort. We also have this draw sort step. I also forgot to mention here that we also just have like a little debug message here for when the sort finishes, just so we know that a sort finished properly. We can go down here to have, this is that angel sort that Zach was talking about. And I failed to mention in the other ones, we also have this play sound function, which we'll see showcased later. This just plays a certain sound file based on the height of the node that's being sorted. So we'll see how that works a little bit later. Then coming down here, we have quick sort. And then in here, we can also start to see that we're using some utility methods. And we'll take a look at those in a minute as well. This partition method here is what's used for the quick sort. And then we can see our implementation here. We have a beginning and an ending index. That's just so that this partition function works properly, and we can subdivide the array into partitions. And then I think this is the second to last one. So we have cycle sort here, and we have our implementation of cycle sort. Again, that Geeks for Geeks website, very helpful when learning these algorithms. And then our last one here is merge sort, and then we can see that implementation down here. So I'll just give that a scroll. Right, so now we come to some of the utility methods. So then this partition method is just used in the right. So now we come to some of the utility methods. So then this partition method is just used in the quicksort function, which is just it. You can look at the code here, see that, and we have that place sound function again in the draw sort step. And then the last one we have here is this isSorted function, which just checks to see if the array is sorted. Okay, now we're going to look at our parallel processor class here. So this class essentially allows us to enable parallel processing with our sorting functions so that we can subdivide a sort job into a bunch of different subsections and sort them each on a different thread on the CPU. Which enables much faster sorting of much larger sort tasks. So we can just see how that works kind of briefly. So we're going to pass in a total number of tasks. So this is the amount of nodes that are getting sorted. And then we have this array here that is the random array, randomized array of float values here that Zach had shown in that initialize array function. And then we also have a sort type here that we'll see later. And then we'll set up this for loop here, which initializes our parallel processing tasks. So that is essentially what this does here, is that we're copying arrays into different subarrays for each task. And then we're going to submit a new task to a different thread. So, and then this switch case here essentially just takes that algorithm that we pass in, and it's going to set up a new sort on a thread for each subarray we have here. So then we're going to wait for all these tasks to finish. It's just a try catch to make sure that there's no errors. And then once all of the arrays are sorted, we're going to create this merged array here, and we're going to put the sorted subarrays in there, and we're going to call this merge array function to merge all of the sorted arrays together, which down here is this function. We just pass into arrays and the sorter, and we just merge these two arrays, which is what this while loop does here. And then we return that merged array, and then we have this end of sort function that gets called, which essentially just redraws the entire array, sorted array.
Okay, now we're going to talk about the sound implementation within this program. Initially, there was a plan to have the sound file. You would only need one sound file, and you would be able to adjust the pitch dynamically throughout the running of the program. However, this was way too intense, and it actually required an extra core, and this later caused a lot of errors because we were using parallel processing. So these cores that were being used to try to change the pitch of the sound files were interfering with our program. So we had to resort to a different solution. I tried using a Tarsos library for sound files, but that did not compile as well. So I used a Python script in order to generate 100 different pitched versions of a sound file. And I passed those in. I created an array for those right here. And then I made a function called initialize sound files, which gets called at the beginning of the parallel processor. And it takes in this folder that we have called generated WAVs. And it loads in all of these sound files into an array. And then we use the Java clip import to open the audio and play the sound. You can see down here in one of the sorting functions, for example, we calculate the fractional position since our array is 100. So down here we have the function draw array rex, which takes in the quadrant, so we know which portion of the screen we're going to be drawing this array in. This is done because of parallel processing. We are trying to display multiple different arrays getting sorted in different parts of the screen. So we have to separate them with this math. If you see here, we have a loop that increments the offset, and we draw the rectangle each time. And this function has a parameter called pause time, which is not used until the end of sort. So we do a lot of extra stuff there to make it look pretty at the end. So we have a function called draw sort step, which utilizes a clear quadrant function. This function redraws black rectangles at the height of the screen over top of where the white unsorted rectangles are in order to redraw it effectively without using stdraw's clear function, which would make us have to redraw the entire array at once. And this calls the draw array rex function that we just talked about. And if there is a pause time factor, we'll be setting it to green for our little finale display, which is this function right here, end of sort, which is called at the end of the sort. It takes the fractional position, so it plays all the sounds at the same time. As it plays the sounds, it redraws by calling draw sort step in a for loop.
Now that we've showcased the code for the project, we're going to showcase some of the sorting algorithms. So first I'm going to start with something that I know is going to complete kind of fast, just so we can show how the multi-core processing works. So we're going to do a selection sort. Let's put in 2000, and let's put that on, let's say, 4 cores. So we can see here the expected time printout, and let's just give it a run and see what happens. Wow, wasn't that something? So now that we've seen how the parallel processing works, I'm just going to go through each algorithm, and we're just going to sort some nodes and see how they work. So we're going to set a sorted array. So if I put like 5 nodes in here and do it on one core, this will run much faster, and we can kind of see what it looks like when that's done. There you go. So let's open the program again, and let's try a bubble sort. Let's do bubble sort here, and let's do 100 on 1, just so we can kind of see what this looks like. All right, now let's take a look at selection, and I think we can do a little more here. Let's try 1,000 on 1 and see what this looks like. Okay, now let's try a quick sort. Let's do 1,000 on 1. I think this should go by pretty quickly. If it doesn't, we can try another number. Not very quick, huh? Let's try out the last sorting algorithm, which is the cycle. So we could probably do a little more here because this one goes by pretty fast. Let's try like 2,500 on 1. Let's go. And lastly, we did talk about having the merge sort in here. Unfortunately, we were having some issues with the merge sort, so we won't be showcasing that here. I appreciate your time, and thank you so much for watching. I hope you have a nice rest of your day.